How P-18 spoon rest radar systems are manufactured inside military radar factory. The moment the first radar antenna begins rotating inside the factory, the entire building changes atmosphere. Not louder, not more dramatic, just heavier somehow. Because everyone inside knows they are not building ordinary electronics. They are building systems designed to see things most people are never supposed to notice. Aircraft hundreds of kilometers away. Objects moving through storms. Signals buried inside electronic interference. The P-18 spoon rest radar system may look outdated to someone seeing it for the first time, with its giant antenna arrays and Cold War-era appearance. But that is exactly what makes it dangerous. While modern stealth aircraft are designed to evade newer high-frequency radars, older low-frequency systems like the P-18 still remain surprisingly effective at detecting shapes hidden from advanced platforms. And that single fact is why versions of this radar are still being upgraded, manufactured, exported, and modernized decades after its original introduction. Inside the manufacturing facility, the scale becomes obvious immediately. Massive steel antenna structures tower over workers, while huge cable bundles snake across assembly sections like industrial arteries. Unlike sleek consumer electronics factories filled with polished white surfaces and tiny components, radar production feels rugged and unapologetically mechanical. Every section looks built around endurance rather than aesthetics. These systems are expected to survive harsh climates, remote deployments, electrical instability, vibration, and continuous operation under conditions that would destroy ordinary electronics within days. Some radar units remain active for years with minimal shutdown time. That requirement changes the entire philosophy of manufacturing from the beginning. The backbone of the P-18 system starts with the antenna framework itself. Giant metal sections arrive from fabrication areas where steel components are cut, reinforced, and treated against corrosion before assembly even begins. At first glance, the structure looks almost simple compared to modern digital systems. But simplicity here is intentional. The antenna must remain mechanically stable while rotating continuously in difficult environments, sometimes exposed to sandstorms, freezing temperatures, heavy rain, or brutal heat. Engineers carefully inspect weld points and structural tension because even slight deformation can affect signal accuracy later. One tiny alignment issue on a radar antenna can distort tracking data across enormous distances. That level of precision hidden inside such a rough-looking structure catches almost everyone off guard. Then comes the transmitter section, which honestly feels like stepping backward and forward in time simultaneously. Older radar systems relied heavily on analog architecture, and many upgraded P-18 units still combine those older principles with modern digital processing technology. Workers install waveguides, power modules, transmitter cabinets, signal amplifiers, and cooling systems, while engineers continuously test electromagnetic performance. Some parts of the system look decades old in design philosophy, while others resemble advanced computing infrastructure. That strange blend is exactly why these radars survived for so long. Modernization programs often improve processing capability without replacing the entire platform, allowing older systems to remain relevant against much newer threats. One of the most fascinating areas inside the factory is the electronic shielding section. Radar systems operate in environments flooded with interference, jamming attempts, signal reflections, and electromagnetic noise. Because of that, sensitive internal components require careful protection during assembly. Workers install shielding layers around processing modules while testing equipment scans for unwanted signal leakage constantly. A poorly shielded radar can become vulnerable not only to electronic attack, but also to its own internal interference. Most people imagine radar as simply sending out signals and receiving echoes back, but modern systems process enormous amounts of information simultaneously while filtering out meaningless noise. The amount of engineering required just to separate useful targets from atmospheric clutter is honestly insane. And then there is the mobility platform, which becomes critical for military radar systems. Unlike fixed installations, many P-18 variants are mounted onto transport vehicles or trailer systems so they can relocate quickly between operational zones. That mobility changes manufacturing requirements completely. Every cabinet, connector, antenna support, and electronic module must survive repeated transport stress across rough terrain without losing calibration. Inside the assembly hall, vibration testing platforms simulate movement over damaged roads while engineers monitor structural behavior carefully. Massive bolts, reinforced suspension mounts, shock absorption systems, and heavy-duty power connections all exist for one reason. The radar must continue operating even after difficult deployments in remote conditions. The power management systems inside these factories are another world entirely. Radar systems consume enormous electrical energy during operation, especially long-range surveillance platforms. Some sections of the facility focus entirely on generators, voltage regulation units, cooling systems, backup power integration, and thermal management. Heat becomes a serious problem because radar transmitters generate massive energy loads during continuous scanning operations. Cooling failures can cripple detection capability quickly, which is why factory testing here becomes extremely aggressive. Engineers push systems through prolonged operating cycles while monitoring thermal behavior under simulated battlefield conditions. Reliability matters more than appearance in every corner of this production process. What surprises many people is how much software now controls systems originally designed generations ago. The modernized P-18 platforms include upgraded digital interfaces, automated target tracking, signal processing improvements, electronic countermeasure capabilities, and integration with broader defense networks. That means software engineers now work alongside traditional radar specialists inside these facilities. Entire rooms filled with monitoring screens analyze simulated target environments while developers refine detection algorithms and filtering systems. The radar itself may look old from the outside, but internally, many upgraded units operate with far more advanced computational support than people expect. The testing halls might be the most intimidating sections of the entire factory. Completed radar units undergo extensive electromagnetic calibration inside controlled environments where engineers simulate aircraft signatures, electronic interference, weather effects, and long-range tracking scenarios. Giant rotating antenna systems sweep slowly across test zones while operators analyze signal returns in real time. Some calibration processes continue for hours because military radar performance cannot rely on assumptions. Small signal errors become enormous tracking mistakes over long distances. That pressure explains why final testing teams move with such concentration around every system. And despite the age of the P-18 design, factories producing or upgrading these systems remain active because modern warfare keeps proving one uncomfortable reality. Older technologies do not always disappear when newer systems arrive. Sometimes they evolve in unexpected ways. Stealth aircraft reduced visibility against certain radar frequencies. But lower frequency systems still retain detection advantages in some scenarios. That reality pushed multiple countries to modernize radar platforms many experts once considered obsolete. Suddenly, these massive rotating antenna arrays became relevant again in conversations about air defense and surveillance strategy. The result is factories where Cold War engineering principles now coexist with modern digital warfare technology under the same roof. The deeper inside the radar factory the process goes, the more obvious it becomes that this is not ordinary manufacturing. Every section feels built around one brutal requirement: the system cannot fail when deployed. Consumer technology gets replaced every few years. Military radar systems are expected to remain operational through decades of upgrades, transport cycles, harsh weather exposure, power instability, and continuous scanning operations. Some P-18 units around the world are operating on platforms originally designed generations ago, yet modernized versions continue detecting targets in environments filled with electronic interference and increasingly advanced aircraft. That kind of longevity changes how every component is manufactured from the beginning. One of the most intense areas inside the facility is the Signal Processing Integration Hall. This is where the radar starts becoming intelligent instead of simply mechanical. Massive racks filled with processors, receivers, converters, and digital analysis modules are installed into the operational cabins while engineers monitor waveforms across multiple frequencies in real time. The amount of data flowing through these systems is unbelievable. Raw radar reflections alone are meaningless without proper filtering, interpretation, and classification. Birds, weather disturbances, terrain reflections, atmospheric conditions, civilian traffic, and electronic noise all create clutter constantly. The radar must separate actual threats from everything else while maintaining stable tracking across massive distances. Watching operators refine those systems inside the factory feels closer to advanced computing research than traditional defense manufacturing. The communication systems section tells another important story. Modern radar platforms no longer operate independently the way older systems once did. Upgraded P-18 units are often integrated into larger defense networks where information moves instantly between command centers, missile systems, aircraft tracking stations, and surveillance platforms. That means every radar leaving the factory must communicate securely and reliably under difficult conditions. Engineers test encrypted transmission systems, backup communication protocols, and synchronization timing repeatedly because delayed or corrupted radar data can create enormous operational problems later. Some of the cabling inside these systems looks excessive until realizing the radar is designed to maintain functionality even if certain connections fail during deployment. And then there are the operator cabins, which almost feel disconnected from the giant rotating antennas outside. Inside these compartments, the atmosphere changes from heavy industrial machinery to concentrated digital monitoring. Multiple display systems, control panels, signal analysis interfaces, and tracking consoles surround operators while simulated targets appear across the screens. Older radar systems once relied heavily on analog displays and manual interpretation, but modernized platforms now use digital visualization systems capable of tracking multiple targets simultaneously with far greater efficiency. One thing the factory never allows anyone to forget is how physically demanding these systems still are despite modernization. The P-18 radar uses enormous antenna structures that require careful balancing and rotational stability during operation. Workers inspect motors, gear systems, hydraulic supports, rotational bearings, and structural reinforcement constantly because mechanical failure in the field could disable the entire platform instantly. Unlike small compact electronics, radar systems combine massive moving structures with highly sensitive digital technology at the same time. That combination creates endless engineering challenges throughout production. And honestly, one of the strangest things about the P-18 production process is how old and new technologies coexist without contradiction. Certain sections of the radar architecture still follow engineering principles developed during the Soviet era, while nearby processing systems use modern computing hardware, digital filtering algorithms, and updated software interfaces. In most industries, that combination would feel awkward or temporary, but here it feels intentional. Military systems evolve differently than consumer products. Reliability often matters more than chasing trends. The transportation preparation area reveals another side people rarely think about. Once assembly and testing are complete, radar systems must be packaged, secured, and prepared for movement across long distances under unpredictable conditions. Antenna sections fold into transport configurations, while sensitive electronics receive additional reinforcement for travel. Some units may cross deserts, mountain roads, muddy terrain, or remote deployment zones before becoming operational. Factory teams carefully secure every module because transport damage alone could compromise calibration accuracy later. The amount of preparation required just to move one radar system safely is enormous. Another fascinating detail is how much manual expertise still exists inside these factories despite increasing automation. Skilled technicians inspect solder points, align antenna components, calibrate transmitter behavior, and fine-tune sensitive systems using experience developed over years of work. In some areas, veteran engineers can recognize abnormal radar behavior simply by observing waveform patterns that automated diagnostics may initially overlook. That human layer remains critical because radar manufacturing combines electrical engineering, mechanical stability, software integration, electromagnetic theory, and operational practicality all at once. The factory may not look futuristic in the way people imagine advanced technology should appear. There are no glowing science fiction laboratories or sleek robotic assembly lines everywhere. Instead, there are giant antennas, reinforced cabins, thick cables, rugged machinery, heavy transport systems, and engineers surrounded by endless streams of electromagnetic data. But hidden inside that rough industrial environment is decades of accumulated radar knowledge still shaping modern surveillance and defense systems today. And maybe the most interesting part of the entire P-18 radar story is that systems like this were never supposed to remain this relevant for this long. Many military analysts assumed older radar platforms would gradually disappear as newer technologies replaced them. But real-world conflicts and modern stealth developments changed that conversation completely. Suddenly, low-frequency radar systems that once looked outdated started becoming valuable again because they could still detect patterns and signatures newer stealth designs tried to minimize. Walking through the final inspection zones inside the facility feels very different from ordinary manufacturing environments. There is no flashy presentation or polished showroom atmosphere waiting at the end of production. Instead, engineers perform one final series of calibration checks while giant antennas rotate slowly under controlled conditions. Signal stability, target acquisition consistency, rotational synchronization, communication reliability, thermal performance, and power distribution systems are all verified repeatedly before deployment approval. The atmosphere feels focused almost to an uncomfortable degree because everyone understands the purpose of these systems once they leave the factory floor. Reliability here is not marketing language. It becomes operational reality. The radar vehicles themselves almost look intimidating once fully assembled. Massive antenna arrays folded into transport position, reinforced support systems underneath, communication modules packed inside armored compartments, cables routed across every section with brutal practicality rather than aesthetics. Nothing about the design tries to appear modern in the consumer technology sense. Everything exists for durability, detection capability, mobility, and continuous operation. Even the cabins feel built around function first, with operators surrounded by monitoring systems instead of comfort-focused interiors. What really stands out is how much invisible work exists behind every radar scan people see on a screen somewhere. A single rotating antenna sweeping across the sky represents years of electromagnetic research, software refinement, mechanical engineering, structural manufacturing, thermal management, communication integration, and calibration testing all working together at the same time. Most people only notice radar systems during military footage or defense documentaries. But inside factories like this, the complexity becomes impossible to ignore. Every signal transmitted and every target detected depends on thousands of manufacturing decisions made long before deployment ever begins. And despite all the attention placed on futuristic drones, artificial intelligence, stealth aircraft, and next-generation weapons, the reality is that radar still sits at the center of modern military awareness. Detection changes everything. Information changes everything. The side capable of monitoring the battlefield more effectively often gains advantages long before direct engagement even begins. That is why radar factories continue evolving quietly in the background while more visible technologies dominate headlines. The P-18 spoon rest system represents something larger than just one radar platform. It represents how military technology evolves in layers instead of clean replacements. Old systems adapt. New systems integrate. Proven designs survive longer than expected. Factories modernize existing platforms while quietly preparing for future threats at the same time. And that mixture of old engineering principles with modern digital capability creates systems far more complex than their appearance suggests. So while the outside world focuses on fighter jets cutting through clouds or missiles launching across the horizon, factories like this continue operating behind the scenes, building the systems designed to see it all first. Like the video if this changed how you see military radar technology, Subscribe for more deep dives into advanced factories and engineering systems, and comment below which military production facility should be explored next.